There are more types of diffusers for cars than you can poke a stick at, but which one is best and how do different designs work? Today we're not only going through a bunch of different designs, but we're also looking at a study that covered several different ones, including some that are now almost mandatory on supercars. So for example, this particular type you can see in figure 10 in this blue section. What is the purpose of these vanes? And that and more is what we're going through today. To do all that, we're looking at this study called, if I scroll up, a numerical aerodynamic analysis of the effects of rear underbody diffusers on road cars. And it is open access, so you can find the link below. And arguably more effort has gone into diffusers across the automotive industry than really any other part of the car. For example, in figure 1, we see a basic F1 car shape. And in F1, the diffuser is everything. If you have a good diffuser, your car is probably going to be good. If you have a bad diffuser, then forget about it. Just start again. So in this figure, we can see that the basic diffuser is this gray part here. It starts from around where the driver's feet is and then extends to the back of the car. This basic diffuser is quite simple to understand. It literally takes advantage of the Bernoulli's principle and venturi effect, where as you increase the cross-sectional area of this diffuser, the velocity reduces and the pressure increases. So under the driver's feet, there is almost no clearance between the ground and the start of the diffuser. It's very close to the ground. As such, the flow is forced to go through a small opening, which means that it has to speed up a lot. As such, the pressure then drops. That creates downforce. As the flow makes its way to the rear of the car, the cross-sectional area increases more and more, and that increases the pressure, which helps reduce the drag of the car. So the basic idea of the diffuser is that simple, but there are so many things you can do to change its performance. One increasingly common variation is sealing skirts. So what is a skirt on a car? So when you say a car has a skirt, we usually mean that at the sides of the car, there are now these sheets coming down to the road. That helps segregate the flow under the car from the flow around the car. As such, this helps us manipulate the flow under the car without interfering with the outside flow and having the outside flow come in and spoil what we're doing underneath. So that is the basic skirt, but as figure 11 shows, so if I scroll down to figure 11 here, these skirts can be diagonal as well. So in figure 11, we see, zooming in, these little parts here, these vertical parts coming down, and they can be diagonal. You can see they shoot off a little bit. So we see the main skirt approaches the diffuser as one piece, then it starts to divide, and now we have two strips on each side of the car. The benefit of these sealing skirts has been shown time and time again that they can increase the car's downforce by over 30%, a huge amount. But they're also very dangerous, with their use in being F1 being the quintessential example of what can go wrong. So skirts were all the rage back in the day in F1. They allowed cars to go around corners way faster because the cars then sucked down to the road. The problem with these skirts though were that if the car hit even a small bump, the car would then lift up, thereby compromising the seal the car had with the road, and outside air would rush in, increase the pressure underneath, and drop the downforce dramatically, and hence the entire diffuser would just underperform. As such, the driver would experience massive losses in stability, which resulted in the car losing traction and even crashing sometimes. This is the extreme case of these seals, and that then led to very strict rules governing what you could and couldn't have in terms of these skirts. But there are many more things you can alter on a diffuser other than just having a skirt. One very important geometric parameter is the angle of it. So in figure 3, if I scroll up here, we see the angle of this diffuser can change. We have the back here and the angle that it goes. That is an important feature. In figure 8, for example, we see the flow vis results of the diffuser at different angles. So I should mention that these diffusers are quite basic in that they don't curve. They're literally just a flat plate going straight up at an angle. And in figure 8, we see that as the diffuser tilts to greater and greater angles, the flow over this one goes from being very well behaved, this one here, to going very not well behaved at all, and being somewhere in the middle. So at 5 degrees, we see that in the middle, the flow travels here very nicely, and on either side, there is a vortex that grows as we head downstream, and it takes up more and more of the diffuser space. At 10 degrees, it seems that the left vortex is now burst, while the one on the right is still kind of traveling along, but it seems to be quite a bit smaller and even maybe not existent really. Then at 15 degrees, the flow is now quite well behaved, but we see a separation bubble just at the start of the diffuser. This is very reminiscent of airfoils where you have separation bubbles on the first half of the surface. So just from this, you can tell how sensitive the diffuser is to its angle, and much of this sensitivity is because of the energy the flow has when it enters the diffuser. So the more energy it has, the more it can stay attached, and you can run the diffuser at more aggressive angles. So when studies report that there is a sweet spot for this angle, where lower or higher angles give worse results, this is very much because of the energy the flow has when it enters the diffuser. Moving on from the diffuser angle, the height of the car off the ground also greatly affects how much downforce you can produce, and also how important the diffuser will be as well. So we can see in figure 4 here, we see that getting closer and closer to the ground results in a disproportionately larger downforce. So there are many things that can affect a diffuser's performance. In figure 5, we see the general pressure coefficient over the underbody of a car with and without a diffuser. The red line is for when the car has no diffuser, and the black line is when it does have a diffuser. So the lower the value of Cp, the pressure coefficient, the greater the downforce. And if you want to find the entire downforce contributed by the underbody to the car, you just need to integrate the area under the curve, so this area here. From that, it is very easy to see that with a diffuser, so the black line, there is much more downforce being produced. You can see so much more area under this curve, or over this curve, I guess you can say. So what we're looking at today is that these researchers are focusing on a realistic car, as shown in figure 9. So it's not an armored body, it's kind of a realistic car. It's not completely accurate, but it's pretty close. And they focused on 4 different geometries. The first was the baseline model, which didn't feature a diffuser, it just was a flat underbody. The second configuration was a venturi diffuser, so in other words, a regular diffuser, and this was set at an angle of 7 degrees. So the reason for this angle seems to be that another research group concluded that this was the best angle for a diffuser. But as I mentioned earlier, this is really not a global conclusion. Sure, for some cars, 7 degrees would be optimal, but it also depends on the rest of the underbody, the ride height, and even the front of the car and how it divides the flow, not to mention all the other small stuff such as the wheel wells and even turbulence. Anyway, their third configuration was this regular diffuser, but also, as we see in figure 11, these side skirts and diagonal skirts. And that's to better channel the flow into the diffuser. I mean, hopefully it does. We'll see later on whether it does or not. So the fourth configuration is the regular diffuser, but without skirts. And on the left here, you can see these front diffusers. So you can see this is the front of the car, and we have cutouts, one on each side of the middle of the car. These are front diffusers here. So do any of these configurations work? Let's find out. To investigate this, these researchers did some CFD simulations. They ran them in RANds, which is lower in terms of quality than what the industry standard is now. I mean, DS is very much the industry standard, and even IDDS for that matter. So does that affect how much we can trust the results? Well, yes, it does. But let's go further into the CFD setup, because concluding how much we can trust the results requires more information. So they used the K-Omega SST terminus model, which is a good selection. So that is a setup.
In figure 12, we see their domain setup, and some good points about it are that the inlet and outlet are placed quite far away from the body, as are the top and side wall. One major problem with the CFD is that they only simulated half the model. They put a symmetry plane down the middle of the car, as you can see here. Now, this is a big problem because car wakes are very symmetric. Axisymmetric, or asymmetric, I should say, sorry, not axisymmetric, asymmetric. But funnily enough, it is only asymmetric in time. So if you were to time average the wake, then it becomes symmetric, especially if the car itself is not completely symmetric. For example, if the underbody isn't symmetric, then you're not going to get a symmetric wake with time. But if it is symmetric, the entire body, then you will get a symmetric flow if you average it over time. So the use of RANs here then becomes not that big a deal, because the symmetry plane kind of negates some of the problems with the RANs approach, because it's time averaged anyway. So ironically here, 2 wrongs kind of make a right, I guess. So the Y plus value was 40, which is okay considering that they are using the K-Omega SST terminus model. But as we all know, a lower Y plus value would have been better still. So it becomes very clear that this CFD was done on a tight budget. At least that's the impression I'm getting so far. The question then becomes whether it is accurate enough to show any real results. And we'll find out later in the results section if that is the case. So just quickly, if you want to learn how to do OpenFOAM, then check out our OpenFOAM link below. But onto this CFD, in figure 13, we can see the refinement regions around this half model car. They look pretty decent. So the car itself sits in the most refined region here, and then there is this refinement region in the wake,
And the general standard for the automotive industry is pretty close to this, but the wake refinement zone should be about the same fineness as the zone around the car. But this one is still pretty good. So they did a grid convergence study, and the main parameters that they were interested in, at least, was the drag coefficient. And this is denoted in table 1 by the Greek letter phi. One interesting thing that these authors did was that they took the finest mesh as the mesh that they're going to use for the rest of their CFD. Now, this is a little wrong to do because while they have a bunch of metrics indicating that the CFD is converging as the measure is getting finer, the fact that they didn't do any finer meshes and they just went with the finest mesh here suggests that it hasn't converged completely yet. So they really should have tested an even finer mesh just to see what the results are. As it stands, from these phi values, there is about a 3% difference in the drag coefficient between the second finest and the finest meshes, so phi 1 and phi 2. As a result, the mesh that they used here was 6.7 million cells. Now, generally, these errors would have been too large for industry simulation, but there is a big difference here, and that is that they are looking at features of the car that greatly affect the car's aerodynamics. They're not small features that only make 1 or 2% difference. We're expecting quite large differences, potentially at least, greater than 3%. So this error should be generally acceptable. At the very least, I think the general flow is okay, and the more similar the coefficients are, then the less we can really trust them. So they could have definitely done a much better CFD setup. Actually, what we're finding now is because I was under the impression that they were strapped for computational resources, but they mentioned just below table 2 here that they used a workstation with 12 cores and 32 gigabytes of RAM. So the RAM is really good. With 32 gigabytes, you can do like 25 million cells, no problem. The 12 cores is a little sparse, but based on their current CFD setup and convergence criterion, I estimate that the time to complete one simulation is probably a couple of days, probably less even. So they could have easily not made their car a half model and actually simulated the entire thing. That would have bumped up the number of cells to about 13 million. They could have also switched to URANs, and overall that might take like a week to run one simulation. So to run all the simulations in this paper might have taken a couple months overall if they did a better CFD setup. That's pretty decent. I mean, if you were to compare that to typical papers in the automotive industry, usually to run all the simulations in one paper requires like 6 months or even more. So 2 months would have been still really good here. So they could have done a bit better, I think. With their CFD setup, I would be surprised if their simulation time for their entire paper would have been more than a couple weeks as it is. Anyway, these researchers set the thermal intensity to 0.15%, which is really low, and I'm not sure why I selected such a low thermal intensity. They aren't really validating their CFD with any experimental work, so there's no need to match thermal intensities there, and this thermal intensity isn't really reflective of real life. But maybe they just wanted to keep it consistent with typical automotive wind tunnels, I don't know. The Reynolds number for this car was 4 million, which definitely puts it in the turbulent range. Now, with all of these errors in the CFD and even the lack of validation, is the CFD worth anything? Well, in table 2, if we scroll down, we see the results. And for the drag coefficient differences, I would definitely say not, because the drag coefficient of each diffuser setup is within a few counts of each other. And even if they were to run a proper automotive simulation with a DES simulation of 250 million cells, this difference would still be in the uncertainty. So the differences in the drag coefficient here don't really mean much, but the lift coefficient is a different story. So the lift coefficient varies by hundreds of counts, and so I'm inclined to say that the lift coefficient data can be generally trusted, at least the trends can be. So we can continue with the results and look at how the diffuser affected the lift coefficients. So from table 3, we see that the baseline car has almost no lift. The lift coefficient is minus 0.047, which I think is within the uncertainty of the simulation. But all the other diffuser setups greatly dropped the lift coefficient of the car. We're seeing values down to minus 0.887, which is huge. So overall, the drag coefficient, the diffuser with the venturi skirts performed the best. However, given the uncertainty in the simulation, I would say it's kind of neck and neck between this setup and the diffuser with the front diffuser as well. Their lift coefficients are both pretty similar, and I think would be within the uncertainty of the CFD. Either way, it shows that both having a venturi skirt and a front diffuser greatly increases the downforce of this car compared to just the typical diffuser and nothing else. So in figure 16, we see the differences the different diffuser setups had on the wake. There are noticeable upticks when the diffuser is present. So we can see the wake pops up a bit more here compared to the baseline. Also, the lower vortex occupies more space with the different diffuser setups compared to the baseline model. If we zoom in here, we can see this little vortex here is quite small in comparison to the diffuser ones, where it becomes much larger and takes up almost half the wake. As a side note, in figure 18, we see the isosurfaces of the criterion around the car. In other words, the vortices created. Now, interestingly, there aren't any A-pillar vortices really present, anything substantial at least. It seems like the edge of the hood kind of takes the place of the traditional A-pillar vortex, with these vortices coming off. And the lack of A-pillar vortices is probably because the front windshield is so angled, so the A-pillars are quite slanted. As such, there's no flow really rolling up into these vortices. In figure 19, we see the pressure distributions around the cars, and from the bottom three figures, which correspond to the three diffusers, these ones here, there is a very clear low pressure at the back underneath where the diffusers are. So here, here, and here, compared to the baseline model where there is no real low pressure zone occurring here. It's just more just a general low pressure as opposed to a concentrated, very low pressure. Over the top of the cars, the diffusers don't really seem to change the pressure much, which indicates that the top of the car and the diffuser flow physics are quite separate here. So for all the cars, the rear spoiler is generating high pressure, which also increases the downforce. So that's pretty nice. I wasn't expecting so much of an effect with just this little spoiler, which doesn't really do much other than just poke horizontally out, but it is there and it's producing quite a bit of downforce. So that's pretty good. So looking underneath the cars in figure 20, and we see the effects of the diffusers are clear as day compared to the baseline. We have the three diffuser setups with the skirts and the front diffuser here in figure D. So the diffusers generate low pressure zones, and if we zoom in, we can see the effects that the vanes have on the diffusers. So you can see these lines going down, and remember how there are these guiding vanes in the diffuser. Now these are these lines here, and we can see the exact effects on the general diffuser here. In each zone, the pressure is localized, which means that each zone is compartmentalized from the other zones around it, and lower pressure can exist there despite what might be occurring in other zones around it in the other vanes. This helps isolate different regions, straighten the flow, and increase the downforce. So for the front diffuser, we can see in figure 20D, this front diffuser bit here, there is a low pressure at the front, but unlike the other two configurations, the low pressure zone is more uniform. Interestingly, behind the front wheels, so here and here, and just inside from the front wheels, low pressure zones form here as well, and are larger than for any other configuration. So we can see some here, but they're not as large and prominent as with this front diffuser present. So the front diffuser affects not only the local region, but also other regions around it and downstream of it. In figure 21, we see the pressure coefficient plots along the car, and to be perfectly honest, I'm not too sure how accurate this plot is, because it shows that the baseline configuration produces much more downforce over the rear part of the car than the diffuser configurations, which doesn't make too much sense to me at least. So maybe this plot is not accurate, or maybe it is accurate and it's just this particular plane isn't showing us expected results. I don't know. I'm guessing that's probably not that accurate. For the upstream part of the car, all of the diffuser configurations produce much more downforce as expected here, but the downstream part is quite wacky. So overall, while the CFD was limited in a few important ways, the general trend seems to be valid, and especially considering that they agree with the theory and what you expect overall. So this study showed that the diffuser is remarkably good at producing downforce, and putting skirts and a front diffuser also helps even more. It almost like doubles the amount of downforce you're getting in this particular case. The guide vanes in the diffuser were quite interesting, and their main function was to compartmentalize the flow and thereby create zones of low pressure and help the diffuser work better. One thing to note is that the distribution of the downforce matters, and diffusers typically increase the downforce at the rear wheels. This is where they are located really, so that makes sense. And that makes the front diffuser quite important too, because it is a flow control device that can be used to help equalize the downforce distribution over the car, and thereby increase the downforce stability, the car stability at high speeds. And with that, we come to the end of this podcast. So if you want to learn how to do OpenFOAM, literally anything from basics to DES simulations to very advanced meshing and dynamic morphing meshing, sliding meshing, then check out our OpenFOAM link below. And if you're doing experiments, did you know that most experiments in aerodynamics has a 2 to 4% error in their data? In our Hawk link below, we go through the math as to why and how to fix that. So that comes to the end of this podcast. If you like to, make sure to click the like button and the subscribe and or follow button, whichever platform you're on. And we'll see you next one. Peace, amigos.